Hi everyone, welcome to today's coding session. Today I'll be solving the network delay time problem using Python. I will explain the problem statement as constraint and the efficient approach we'll be using. We will explore two methods, the Dijkstra algorithm, which is a greedy approach using a priority queue to find the shortest path efficiently. So we're going to use the min priority queue here. And the shortest path faster algorithm, which is SPFA, a more optimized approach to sparse graph to leverage a queue to improve efficiency. As I code, I'll explain each step, how we update shortest path and optimize unnecessary computation. Here's a quick explanation in case you haven't done queues before. So in our case, for the Dijkstra algorithm, since it's the greedy approach, we're looking, if we were to look for the max, in our case it's the min, but if we were looking for the max, as you can see, the red areas where we're going to end up going because they're maximum for their specific levels. But it doesn't guarantee the best choice. That's what this is trying to explain. And again, this is just giving you the path. It's still going to be the minimum path nonetheless, but it won't be the optimal approach. Now to distinguish between a queue and a priority queue, just so you know, first in will be the 3, followed by the 2, then the 1. And same way out. It's going to be the 3 out first, then the 2, then the 1. This being the front of the line. Priority queue, on the other case, still has first in, first out, but when it in-queues, it in-queues based on the priority. So there's a prioritization that takes place. That's the only distinction here. So here's a problem. We have a directed weighted graph representing a network of n nodes where each edge ui, vi, and wi indicates that a signal takes wi time to travel from node ui to node vi. Our goal is to determine the minimum time it takes for a signal sent from node k to reach all nodes in the network. If some nodes cannot be reached, we'll return -1. And here's the example, explanation. So 2, 1, 1 is from 2 to node 1, 2 here, node 1 will take 1, let's say time, it'll take 1 minute, 1 hour to get the signal there. And again, from 2 to 3, node 2 to node 3 is also going to take 1 minute, 1 hour, whatever that 1 represents, any unit. And then from 3 to 4, it's going to take 1 minute, 1 hour, whatever you want. And now our goal is to find out basically what is the maximum time. So as you can see, from 2 being the original is the source because k equals 2. 4, n equals 4 is because there's 4 nodes here and here as well. So k2 is the start point, and our furthest point out is 4. So it's going to take 1 plus 1, meaning 2, to get there. And that's the reason we get the output 2. Now here, for example, 2, we got node 1 to 2. And it takes 1 time to get there. Our starting point is k equals 1. So our output is going to be 1. That's the longest I'll take to get from node 1, our originator, to our destination. And then for example 3, we got the same thing. 1, 2, 1, 2. But here we're starting at k equals 2. And as you can see, there's nothing reaching back to k1, this being the source. So we're going to return -1. That's what we're saying. There's no way to reach this number. Our code will solve this problem. So here are our constraints. So the input consists of a list of directed edges where each edge is representing as ui, vi, and wi. ui is the starting node, vi is the destination node, and wi is the time it takes for a signal to travel from ui to vi. And our goal is to find out what is the longest time it takes to get there. Node and edge constraints is the network consists of at most 100 nodes, meaning the number of nodes n will always be between 1 and 100. The signal will always be sent from a valid starting node k, where k is between 1 and n. Every node label is within the valid range, meaning both sources ui and destination vi nodes are always between 1 and n. There is no self loops. The source and destination nodes of any edges will always be different, meaning ui will never be equal to vi, and non-negative travel times, meaning the time required to travel between two nodes, wi, will always be between 0 and 100. And if any node cannot be reached from the starting node k, we will return -1, as you saw in example 3. And since n is relatively small, less than 100, up to 100, but the number of edges can be large, 6,000, at most 6,000, we need an efficient shortest path algorithm. The Dijkstra algorithm is ideal for handling graphs with positive weight, ensuring a big O of E log B time complexity, and the shortest path faster algorithm can be an even faster alternative for sparse graph. By considering these constraints, our solution will be efficient, handle all edge cases, and find the shortest time to reach all nodes optimally. So we're not going to implement here the brute force approach because that explores all possible paths from node K and will be too slow, especially given that the number of edges can be as large as 6,000. Instead, we need an efficient way to determine the shortest time for a signal to reach all nodes. A more efficient solution is the Dijkstra algorithm, which finds the shortest path from a single source node K to all other nodes using a priority queue. This approach ensures that we process nodes in order of their current shortest path travel time, making it well suited for graphs with non-negative weights like ours. By leveraging a min heap, which is what we'll be using, the Dijkstra algorithm allow us to efficiently update travel time while ensuring each node is visited in the optimal order. So let's implement the code. So here there are two imports that we're going to have to use. We're going to use the heapq, since we're using a priority queue, and we're going to use a dictionary, which since we're using a graph in order to do our problem or solve our problem. We're going to be creating the graph here, initializing it with default, which is going to be empty to begin with. And here we are initializing that graph with, again, our source, our destination, and our weight, which is time in this case. And this is the graph being initialized. Here we got the current time, and our starting node is 0 because that's how long it takes to get there, since this is starting node. And being how many nodes we have, K being the node where we're starting with, and times including all the nodes and their times. And we're going to be using this dictionary in order to track the shortest known time to each node. And here what we're doing is, as long as this min heap is not empty, we're going to loop through this loop. We're going to continue the loop. And here we're going to remove the minimum heap from the heap queue, and we do so by popping it here. We're going to assign the time and the node to it. And what we're doing here is we're saying that we'll skip our processing if we already found the shortest time for this node. So as long as this node's already inside the shortest time, then we're going to skip it and go to the next value, the next node. And the whole goal of this entire for loop is to update our neighbors if a shorter path is found. So here we're going to go through our graph node, which we created here. And we're going to use our node that we basically removed from here in order to find the value. And we're going to assign the neighbor to that node and the time to that node, how long it takes. And then if the neighbor is not in shortest time, meaning we already haven't done this since we're looking for the shortest time, then we're going to enter this loop. And in this loop, now we're going to push into min heap the time to get to this node, the time and the neighbor of that node. So this way we continue the loop until we loop through the entire graph. And here, once we're done with the loop, assuming that we went through all of the nodes on the graph, we're going to say, okay, well, is the length of shortest time the same as n? And it should be if we went through all the nodes in the graph. If we did so, since we have a dictionary for shortest time, right? What we're going to retrieve by using shortest time, that value is the values as opposed to the key of it, which the values are the time it takes from getting from one node to another. And in this case, as we're using max, whatever that value, the maximum value there, meaning the further out node, as we saw in the example here, like from 2 to 4, we're trying to see, okay, how long does it take to get there? 1 plus 1, 2. So the longest to get from 2 to 4 is 2. And that's what the value that this is going to give us. for return. Let's see what the result of this is. Turns out I had a runtime error here. And I forgot to do something very key here, which is basically annotate the shortest time in order to get the right answer. As you can see, this was accepted, all three cases. And let's see how it compares against others. So 369 milliseconds is definitely not the fastest, but it beats 95%. And space-wise is also not that efficient, but nonetheless, this is a great solution just if you're looking for runtime. Okay, so let's go through an example. So this is what happens when we're doing the code itself. First, we initialize the graph, as we can see here. Then we're gonna go through the loop where we got u equals 2, which will be based on the time, the destination being 1, and the weight being 1 as well. And here we're adding the value to the graph itself from time to graph using the key being 2, u, and the weight and the destination v, and then the weight being w placed here. And this is a representation of how it would look: 2 to 1, the weight being 1. And we're doing the same thing again. Now we're going 2 to 3, source 2, destination 3, the weight of 1 as well. And now we're adding it to the graph itself, and this is how it will look. So we already did this one, and now we're going this way. Now we're going to the last one. The connection is from 3 to 4, and the weight is 1 as well. Source, destination, and weight. And then we add it to the graph, and finally this is what the whole graph looks like. So now the mean heap, 0 to k being 2, is what it looks like now. The shortest time, we're just initializing it as an empty dictionary. And now we're starting the loop. We know it's not empty because we just added the value of 0 to it. It takes 0 time to get to 2 because it's a starting point. So now, time and node, we're removing from heap 0 and 2 and placing the time as 0 and the node 2. Now we know that this is our first time iterating it, so we know that node is not in shortest time, as you can see here. And now we actually are initializing it 2 and 0 for the shortest time. So we know to get to 2, it takes 0 time. That's the shortest time possible. And this is where we're currently at right now, just creating our original node. Now we're going to iterate through the graph itself, which will be here. And we have from 2 to 1, weight being 1. And that's where we got the source and the target, followed by the weight. Again, is the neighbor, meaning is 1 inside shortest time? No, this is our first time doing it. And now here, we are going to push 1, 1, which is what we had here, into the min heap. So we're going to add 0 plus 1, travel time 1, and we're going to get 1 as a time and 1 as the node that we're going to from 2. And again, we're going to do the same thing. We're going to go from neighbor to travel time, and we're still on node 2, so this time is node 3, travel time is 3, source being 2, target 3, and time 1. And we know that neighbor is not in shortest time because it's our first time processing it, and as we can see here, it's not there. And now again, we're going to push it into the min heap. Again, is 0. We're adding our current time from 2, 0, which is our time at node 2, plus 1, which is to get from node 2 all the way to node 3, which will give us 1, 3. And now that we're done processing that, now we're going to go back to the min heap, and we know that it's not empty. And in this case, since it's priority queue, we're going to take out 1, 1, which is what's happening here. We're going to pop 1, 1, time will be 1, no will be 1. And we know that no is not in shortest time, as you can see here, since we haven't processed it before. Our shortest time is now going to be initialized. 1, 1, as we had node 1, time 1. And this is how it looks like. From going from node 2 to 1, it took 1 unit to get there. And again, here, now we're going through the loop, and now we have node 1, and we know there's no connection. Node 1 is not connected to anything, as we saw here. there is no connection in that direction to node 1. Since there's no connection, we will return an empty array. And we go back to the min heap. We know that there's still values in it. Now we pop out that value and we place it into time and node. And again, node is not in shortest time. 3 is not here. So that's not going to skip it. And now we initialize the shortest time, which would be node 3. From 2 to 3 is going to take 1. And now we're going to add it in our next loop. So here from 2 to 3, it takes 1 unit of time to get there. And now, as you can see, it is added to the shortest time. Again, we're at node 3, and that's going to help us with the graph here, because we're going to go at node 3 to get a 4. It takes 1 unit of time, and that's what this means right here. So now is neighbor, which is 4, in shortest time. As you can see, it's not here. So because it's not here, this will return true, and we're going to go into the if statement. The if statement is also going to update mean heap with 2, 4. And this is saying that from 2, in this case 3 to 4, we're going to add, since from 2 to 3 it took 1 unit, and from 3 to 4 it took another unit. That's why we're adding 1 plus 1, so it'll give us 2. To get the signal from the source, which is 2, to 4, meaning from 2 all the way up to 4, it's going to take 2 units of time. And that's why we initialized it 2 to 4. And next, as you can see, our main heap now has 2 to 4. So it's not empty. And now we're going to empty out the mean heap. And we're going to give it to time of 2 and node of 4. And now we're here. Is the node in shortest time? No, it's not in shortest time. So now we actually are going to update shortest time. And this right here is our final list, showing everything, how we went from node 2, how the signal propagated from node 2 all the way up to the last node, which is 4, which here it takes 2 units of time to get to the signal to get from node 2 to node 4. And this is how it looks. So we started node 2, sent the signal out, it got to node 3 at 1 unit of time, and it got to node 4 at 2 unit of time, which is 1 plus 1, which is what it used to be when we constructed it. So now again, when we go for node equals 4, we know that there is no further connection. As you can see here, there's no further connection to 4. So because of that, we're going to get an empty array in both scenario. And now we go back to min heap, see if it's empty. It is. So now we're going to get out of this loop. And now what we're going to do here is we're going to say, okay, well, is the shortest time, well, if length is short and shortest time equal to n, and in this case, we know that it has 1, 2, 3, and 4 value. And we have 4 total. So yes, they're equal to each other. So now we're going to find the maximum value here to show how long it took to get to the last node. And it took 2 units of time to get there. And that's what we're going to return, 2. I hope this walkthrough helped you understand how to efficiently determine the minimum time required for all nodes to receive the signal using the Dijkstra algorithm. If you found this valuable, don't forget to like, subscribe, and stay tuned for more in-depth coding tutorial. Now let's explore the shortest path fastest algorithm, also known as SPFA, which provides an alternative and potentially more efficient way to solve this problem, especially for sparse graph. Okay, so again, this is what we're going to be using a queue. So as you know, it's first in, first out. So this guy was first in, and he'll be taken care of. And again, this is the same example as I introduced at the beginning. So the shortest path algorithm is an optimized version of the Bellman 4 algorithm that uses a queue instead of a priority queue. This allows it to efficiently update shortest path while avoiding unnecessary computation. The SPFA performed particularly well when the graph is sparse. It has fewer edges compared to nodes, making it a strong alternative to Dijkstra algorithm. So let's implement this code. So in this case, since we're using a queue, we're going to need to import deque, and we're still going to use a graph, so we need this. We're still going to need this part of the graph. We're still building the graph the same way as the Dijkstra algorithm, so this is not going to change. And here we're initializing the distance travel. And from the beginning, everything is going to be initialized to infinity, positive infinity. And here we're also initializing, after this is complete, now we're going to initialize k, which would be our starting point, to 0, since we know that's going to be where we start, is always going to be 0. And we're also going to initialize q by dequeing 2. So this part of the algorithm is very similar to the Dijkstra algorithm. Again, if the queue is not empty, we're going to loop through it until it's empty. And the first thing that we're going to deque or pop left is going to be the queue, which already was initialized with the starting point, since we're doing breadth first search in this case. And in this part of the code, we're doing very similar to the Dijkstra algorithm again. We're going through the graph itself. We're going to initialize neighbor and its weight. And here we're saying, okay, well, is Dijkstra node, which we got here, plus the weight, is that one less than the distance neighbor, this neighbor over here? If that's the case, we're going to initialize it with the distance, with the goal of getting the shortest distance possible to get from one node to another. And then we're going to append the neighbor to the node, and then we're going to go back and we're going to loop through it. And I'll walk you through in more details with a detailed example. And very similar to our previous example here, what we're doing is we're going to get the value of distance, which originally here were all infinity. And through this code that we're modify, and hopefully by the end of the algorithm, what we end up having is when we do this comparison where mass time does not equal the positive infinity. Because if it does equal positive infinity, then we're going to return -1, meaning there's no way to get from one node to the other. But since it doesn't equal -infinity, it's going to give us the max value. And let's see how it performs. And here I did a key error. I named it I instead of 1. As you can see, it was accepted. No error here. Now let's see how it compares against other people. This is a little bit faster runtime. The other one was 369 milliseconds. This one's 363 milliseconds. Percentage-wise is on par. But as you can see, memory-wise, this one does a lot better in this case. Still not as, it could be much better. But nonetheless, this is a pretty good, very efficient approach. So now let's see example walkthrough. Again, we already did this part where we initialize, create an empty dictionary. We're initializing it here, and this is what it looks like. So there's nothing different in this case. And now we're going through each value, and I'm going to give you a walkthrough for this one, because here we're initializing it to positive infinity each step of the way, positive infinity all the way. And now here for distance k equals 0, now we're going to show it as 0 because that's only takes 0 time to get to 2 since that's our starting point. Now we're going to deque 2, which is our starting point, again to q. And now we know that q is not empty, so we're going to be able to enter the loop. Now we're going to remove from q the number 2. And now we're going to go into neighbor, look at the graph, and see that when we use 2 as the key, we'll get the next node being 1 and the weight 1. And again, here is showing you a detail of distant node being 2, and that value is 0, and it's saying plus weight. And our weight is 1. So 0 plus 1 is going to be less than distance neighbor. Distance neighbor is positive infinity, so yes, it's going to be less than that. So we're going to enter the loop or the if statement, and here now we're going to give the value of distant neighbor. We're going to update it by giving distant node, which again is 2, so 2 equals 0, plus the weight, which equals 1, so that's going to give us a value of 1 here. And we're going to append the neighbor to the queue, which is 1. So the neighbor of 2 is 1, and we're appending it to the queue. We're going through the for loop again, and 1 has no neighbor. So here it's saying it's distant node, which would be 2, and we're still dealing with 2, which is 0, and plus the weight of 1. Is it less than positive infinity? Yes, it's true. So we're going to enter the loop again. And here, we're going to do the same thing, which is, okay, distance neighbor, and neighbor being 3, will give us infinity. And we're going to initialize it with a new value of distant node 2 plus the weight, which will also give us 1. So the distance from 2 to 3 is going to be 1 again. And we're going to append 3 to the queue. So we got 2 value now in the queue. We're going to go back to the while loop, which we know that the queue is not empty. Then now we're going to just do the first in, first out with no priority or anything. 1 being the first one that's going to be taken care of. Queue will be left with 3. And again, the graph doesn't have, as you can see, if you look for 1 in the dictionary here, there is no key value for 1. Therefore, that's the reason we're going to get the empty array. Now we go back to the queue. We also remove that one, 3, in this step. And the queue is empty. And now we know that 3 does have a neighbor. It's a neighbor to 4. And the weight, the unit time to get there is 1 unit time. Now we're saying, okay, it's distant node being 3, here being 1, plus weight, which equals 1. So now we're going to add 1 plus 1, which will give us 2. Is it less than infinity, positive infinity? Yes, it is. And now here we're going to update the neighbor being 4. So 4 currently is, as you can see here, is infinity. So now we know distant node being 3, the node being 3, so that's 1, and this is where we get the 1. So 1 plus the weight of 1, that gives us 2. So we know that from the original node 2 to 4, it's going to take 2 units of time to get the signal. We're going to append 4, and now we know that it's still not empty, and we're going to deque it. And again, there is no connection from 4 to any other node, so this loop is not going to iterate. We'll go back to the while loop, and now we're going to extract the maximum value between 1, 0, 1, and 2, and we know 2 is the maximum value, as we can see here. So return 2 for max time. And now our question here is max time not equal to flow infinity? So yes, if max time was updated, its value is 2, and since that's the case, it returns true. We're going to return 2. It takes 2 units of time to get from 2 to 4, from node 2 to node 4. And here is a performance for the 2. Dijkstra algorithm performs well, but is a logarithmic factor, makes it more efficient in the SPFA in many cases, so in terms of time complexity. And shortest path faster algorithm, worst case, is big O of V times E, whereas the Dijkstra algorithm is big O of B plus E. And as you can see here, this is showing us in the line that performance-wise, time-wise, is not supposed to be as fast. And as you can see on LeetCode, it showed us this was faster, but again, performance is not necessarily indicative of worst-case scenario, which we know that in the long term, SPFA is not the best choice, but is a good option for sparse graph. Now, in terms of space complexity, they're both equal. So since they're both equal, it's not really a factor. So nonetheless, as the number of edges increases, the dense graph space usage grows significantly. All right, if you really enjoy my content, comment, subscribe. If there's any problems you'd like to solve, let me know. Otherwise, happy coding and see you next time.